Okay, folks, good morning. This is Todd Coburn of Cal Poly Pomona with lecture 13 of ARO3261. Today we're going to continue our study into beams, and we're going to look specifically at the elastic curve and how to calculate deflections and slopes of beams subjected to transverse loads. All right, remember last time, or actually 2 lectures ago, I think, we looked at a straight beam that we then bent with pure bending. We took a look at the strain distribution of the beam. We compared similar triangles of the radius of curvature to the distance from the neutral surface to the extreme fiber. We took a look at the force per strip, per individual little strip of the element of the cross section, the moment associated with that, the total moment on the section. We put all this together, shuffled it around and rearranged, and we came up with these fundamental equations for the stress anywhere in the cross section, or the allowable moment if we insert the stress allowable. Now we're going to be continuing today this discussion and using this to develop what we're going to need to calculate slopes and deflections. So we bent in our original derivation, we came up with this m over I is related to the E over R, radius of curvature relation, which we can rearrange. Take a look at a little incremental element. Note that the little ds is related to the radius of curvature and d theta. Rearrange that. When our beam is initially straight, if our d theta is extremely small, tiny small, smaller than it will often be, but we'll pretend it's always true, then this relation is true, which we can write this way. If we take a look at our little axis of the beam and the deflected shape, we find the relation tangent theta is equal to dy over dx, which we often will say, gee, if our angle is small enough, then theta is just tangent of theta. And if we use all these gross simplifications and assumptions and rearrange, we get this 1 over the radius of curvature is equal to m over EI. When we realize that this moment is not just the moment at a point, it's the function of the moment across the beam in the span that we're looking at, that deflection, that relative deflection, then we get these two relations. We find that the change in the slope of the beam, so the beam is straight and it goes into a curved shape. The tangent, or the angle of the tangent with the beam, is the slope, and the slope of that beam at any point, the slope of that beam, the change in that with respect to a little increment of length. So the change in slope over a little increment dx is just the function of the moment in that area over EI. So if we have an equation for the moment of the entire beam, we could take a look at the change in slope over any little element. And in the same way, we find that the change in the slope, or the second derivative of the deflection, is equal to the m of x over EI. Now these two relations are going to be critical. We're mostly not going to be taking the derivative of the slope equation or the second derivative of the deflection. What we're going to do is write our equation for the loading, integrate it to get the shear, integrate it to get the moment, integrate it again as we divide by EI in order to get the slope, and then integrate one more time as we continue to divide by EI to calculate the deflection. So these two relations are what we need. The elastic curve is what we call the equation for the deflection of the beam. If you write the equation for the deflection of the beam, or if you determine it by integrating in this way, the equation you get for the deflection as a function of the length of the beam, that's called the elastic curve. So we have some key relations. Let's take a look at these for a moment. Our change in the slope with respect to x is the moment as a function of x over EI. The second derivative of the deflection with respect to x is the moment, function of the moment divided by EI as well. So these are telling us the behavior of the elastic curve. The actual elastic curve is that equation y of x. Y is a function of the length of the beam or the position on the beam. So if you take a look at this Beer and Johnson picture, the second one, take a look at the first one, figure A, it just shows a beam and the neutral surface. And then in figure B, we see that the neutral surface, if we had the equation y of x of where this neutral surface is relative to the original straight position, that's called the elastic curve. Okay, and then the theta, the slope of that curve, theta of x, is just the derivative of that. Okay, so these can be integrated to get the deflection, which means we can remember this. The theta is simply the 1 over rho, right? The 1 over the radius of curvature. So we've got these two we can just integrate. So let's just say, okay, let's take, since the second derivative of the deflection with respect to x is the moment as a function of x over EI. Remember, we started off by writing the equation for the moment. That's how we got here, right? Or we started off by writing the loading function and integrating to the moment equation. So if we take the equation for the moment and then integrate it and divide by EI, we're going to get whatever the integral of that is, and we have that constant of integration shown as C1 here. Now, I often like to use slightly different nomenclature. I used to like that because to keep these constants categorized and easily recognizable, we're calling that constant of integration C1 here. I also call it, in some of my slides, you'll notice I call it C theta, because what this means is when we take the integral of the moment equation to calculate the slope, the first constant of integration in that step determining the slope is a constant which springs into being due to the slope. Then when we integrate again, we can get another constant, which I like to call C of y, or CV, because some books use V for that vertical deflection. So I like to use C theta for that integration that gives us the slope, and Cy to use that constant of integration that gives us the y. When for shear and moment, I'd use CV and Cm, but remember, we already saw last time that those are always going to be 0 for these beams, just based on the initial conditions. But for theta and for deflection, they're not always 0, so we're actually going to have to do something extra, which means inserting our boundary conditions to calculate what those are. We now can integrate again, which means we've got the second integral of the moment with respect to x. We've got C1 times x, that becomes x, right? And then we've got C2. So C theta x plus Cy. Okay? Now, this gives us an equation. We got a couple additional unknowns. In order to figure out those unknowns, we're going to have to insert boundary conditions, which means we're going to have to understand how to do that. Some of you have done this before, maybe a little bit in statics you've certainly done this in calculus, and you probably didn't really want to learn it, but it's not as hard as it looks. And if you just decide, this is easy, I'm a stinking aerospace engineer, or gonna be one, I'm gonna master this mother so I can pull this into my repertoire of tools, you can do it. There's a whole bunch of calculus that you probably hated and didn't really learn very well. And fortunately, a lot of that calculus ain't going to be used in any kind of practical industry work or even research. But there's a lot of calculus that we need to have mastered in a lot of trig. And they do have practical use in industry. One of them is the simplicity of being able to deal with a couple integrations of a relatively simple equation, including having constants of integration spring out of nowhere, and then determining the value of those by inputting our boundary conditions so that we make this our tool. Kind of like somebody going to war, joins the military, goes out there to war to fight for their country. If they just start trying to use that weapon on the first day of the battle, they're going to be in trouble. Because it's going to jam, it's going to misfire, it ain't going to shoot where they think they pointed it. But a good warrior takes his time to understand his weapon so that he can force it to do what he needs it to do in a time of trouble. In the same way, if you actually mean what you said when you signed up for this aerospace engineering education, you should set your mind to master the tools you need. And one of them is simple calculus ideas like this. ¿Comprende? ¿Te gusta? Nishiwanma? Okay. All right. Now going back and remembering that the shear is just the change in moment with respect to x, and the change in the shear with respect to x is just the negative of the loading. We can see if we differentiate that equation for the, we take the deflection equation for the deflection, we differentiate it once to get the slope, we differentiate it again in order to get the moment, and then we differentiate again to get the shear, and again to get the loading. Now maybe you're starting to catch on here. What this means is if we have an equation for the deflection of the beam, we can integrate 4 times. We're going to get with the, we can differentiate 4 times. The first time we differentiate, we're going to get the slope. We're going to differentiate because that's the change in the deflection with respect to x. We differentiate again and then multiply by EI, or divide by EI, and we're going to get the moment. We do it again and we're going to get the shear. We do it again and we're going to get the loading function. Now the problem is those loading functions are singular a lot of places. So this is more difficult if you try to use the continuous calculus approach that I showed you last time. It's going to be a lot easier if you use singularity functions, since a singularity function makes a singular loading continuous, or at least it makes it so we can deal with it. It actually doesn't make it continuous, but it makes it so that we can deal with it in spite of its singularity nature, okay? Now, another problem is we're actually not going to generally have that equation for the deflection so that we can just simply differentiate. Most of us are pretty comfortable differentiating because when we differentiate, we've got a pretty clear way of differentiating most functions, and anything that looks complicated tends to be blown straight to hell as we're going through it. When we integrate, what we have is a little more challenging calculus operation, and then we've got these miserable constants of integration which we have to get rid of by later imposing boundary conditions. Most of us don't like that, but it's not that hard and you can do it. Now, you can do it doesn't mean you're going to do it in my class this semester. It means you're going to have to force yourself to pull the best out of yourself so that you can nail this stuff. Because you can do it. Let's look further. Done with the pep talk. Actually, that's probably not true, but we'll just pause the pep talk and move on, huh? All right, so here's a couple beams. We can see the neutral surface here, or the elastic curve. They're shown red in here. Few different loadings. And if we look at those, we see, let's see, in this first figure, figure A, we've got 2 pin supports. The first support imposes the condition that deflection is got to be 0 there, and so does the support at B. If we look at the figure B, we find the same thing. 2 supports, both stopping vertical deflection, and 2 of these supports also stop lateral translation. But since there's no loading laterally, we don't actually need to use that. It's not of use for us. We get the third equation. We find out at the left end the deflection has got to be 0 and the slope has got to be 0. So we use some of these ideas back in statics, or a lot of them, but now we're going to take it further because we're going to impose the boundary conditions and use it to figure out what those miserable constants of integration are. If you cannot recognize what the boundary condition is for one of the given supports, you're in trouble already. You need to take as much time as you need to master that relatively elementary principle. Study that, make sure you get it. It's really simple. You just need to take the time to master how to glance and know, oh, pin support, vertical deflection is 0. Fixed support, both the vertical deflection and the moment are 0. There are actually more complicated ones, like when we have a pin in the middle of the beam that give you a 0 moment at a point. You probably won't run into that in this class. There are some undergraduate classes where they'll throw a problem at you like that. I guess I actually could, but not without having pitched that little specific idea to you. Okay, so let's say we have this this equation here. All we would do is impose these boundary conditions that we can see. Okay, now don't worry, we're going to take a look at some examples once I'm done spilling all the beans into your lap. Okay. So here's our basic approach. We're given a cantilever beam. Could be one of these, right? These are two different beams, by the way. We're going to go and we know these relations for the slope relative to the moment and the shear related to the moment and the loading related to the shear. And so if we could just write an equation for the loading, we can just note that that's the fourth derivative of the deflection, which means all we got to do is integrate that mother cuatro tiempos, 4 times, impose boundary conditions, and determine what the constants of integration are. Then simplify our equation. So what's the first step? The first step, here's our systematic analysis approach. This is the key. We're going to write an expression for the loading. What's the easiest way to deal with beams with a loading that's not super simple? Singularity functions. Pull up your singularity function table. Find each and every imposed load, which includes, first we've gone and drawn a free body diagram of the beam. We have removed any constraints and replace them with the forces and or moments that they can translate into the beam. We then are going to write a singularity function term for each and every load moving from left to right for every force, every distributed load, and every moment. We might have to first characterize our loading so that each term appears in that table. We'll look at that a little more again today. We looked at that last time a little bit. Once we have the equation for the loading that includes one term for each and every load that we find from the left end of the beam to the right end of the beam, but not including the right end of the beam. Once again, you can include the right end of the beam, but those terms will never be used, so you can just ignore the rightmost end of the beam for that. Once we have that loading function, we write it, that's W of X. Then all we have to do is integrate that mother 4 times. The first 2 times, we're going to get a constant of integration that pops into being that's always going to be 0. Then the last 2 times, we're going to get a constant of integration, which we're going to have to impose boundary condition to determine what it is. Sometimes it'll be 0, sometimes it'll be something less convenient. Piece of cake. Instead of thinking, oh my gosh, this is so hard, when you see something like that, what you should start thinking is, oh my gosh, this is just hard enough to keep out the riffraff, so I will earn the big bucks that I'm going to make when I master this stuff and get out of here with my miserable degree. Comprende? Okay. So, because this is true, we're going to integrate once for the shear. Our constant integration is going to be 0. You actually don't have to insert a shear value with its position because we know that C1 is going to come out to be 0. Why? Because I told you so. Otherwise, go ahead and calculate it yourself. We're then going to integrate again to get the moment. We're going to have a new constant of integration pop into being, which is also 0. We're then going to integrate again for the slope, and this time we're going to divide that mother by EI. This is what the farmer was singing about, E-I-E-I-O. He was actually trying to calculate the slopes and deflections of beams, and he got it all messed up. So he just made a cute farmer child song, okay? And then we're going to do, now what we could do is we could just integrate again, but we're going to find it convenient if there's any slope constraint on the beam, like a fixity. It usually will be easiest if you go ahead and impose that boundary condition now. That way we can solve for that C theta immediately. However, if there's no slope constraint, then that won't be possible. You will have to keep C theta as a variable and integrate again and then impose two deflection boundary constraints. It's actually more common to have deflection boundary constraints than slope boundary constraints in aerospace, but both are possible. Okay, so if possible, insert a slope position, and then we will go ahead and integrate again. Another constant of integration will come out, and then we'll plug in either one or two boundary conditions to finish analyzing a beam. Over here to the right is a little summary of the different kinds of constraints. We might see a pin constraint, a roller constraint, and a fixed constraint, and a free end, and an internal pin or hinge. That's where we set the moment equal to 0 if we have an internal pin like we talked about, or like I alluded to moments ago. Make sense? All right, we said this is true. Okay, once again, looking at this last equation, we know that C1 is 0 and C2 is 0 for all the stuff we're going to see. It's C3 and C4 that we're going to be solving for. So this is a summary slide showing us our key relations. The fourth derivative of the deflection with respect to x is just the loading over EI, and it's the negative of that. We integrate once for the shear, once for the moment, once for the theta, once for the deflection. Okay, what this means is if we actually had an equation for the deflection, we can just differentiate 4 times to get everything we need. But usually it's going to be the other way around. Here's a sample problem. Say we got a beam like this, and we want the deflection. All we got to do is write an equation for the loading. In this case, we're going to have a reaction at A. We're going to have a reaction at B. We've got an applied force at P. We're going to write, now I think this problem actually solves it the longhand way, like using summing forces and moments with successive free body diagrams. The easiest way to solve this is to write the singularity equation for the loading, W of x. W of x, we're going to have one term for the force, the reaction at A. We're going to have another term for the reaction at B. Both of those are aimed upwards. We're going to make sure the sign coincides with that. The force at P would cause a term to come into being, but actually we don't need it because it's the right end, so we'll just ignore that altogether. Now that we have the function of the loading, we integrate once for the shear, once for the moment, divide by EI as we integrate again for the slope. There's no slope constraints, so we will bring that constant of integration forward, integrate again for the deflection, and now we've got 2 constants of integration. We plug in the boundary constraint at A of the deflection equals to 0, and the boundary constraint at B of the deflection equal to 0, and solve for those 2 constants of integration. Then we will go ahead, simplify our equation, either report our W or Y of x. In this case, we want the deflection. We'd simplify our deflection equation. We can calculate what the maximum is. Remember, you find the maximum by taking the derivative of the function and finding out where it's 0. That gives you a local maximum or minimum. But that's nonsensical work because actually, in this process, we already know what the derivative of the deflection is, and that's the slope. You already have the slope equation, so you can just take the slope equation, set it equal to 0, and that will tell you the locations where you might have a maximum deflection. You can look at the different ones and grab the one that's maximum. Okay? Blah, blah, blah. That's what all this crap says. Okay. Here's how it works. We first calculate our reactions by summing forces and moments, and from our free body diagram. We then go ahead and, as I said, this is just taking successive free bodies. This is the first method I presented last lecture. We'd first take a section cut in the relative AB. We take another section between B and C. That would give us 2 equations for the moment, which gives us a little bit more work. If we'd written a singularity function for this, it would be even easier. Don't worry, we'll look at some of those. There's our deflection of the elastic curve. Remember, since this is using the moment from A to B, this deflection of the elastic curve is only valid from A to B, not from B to C. We can then integrate that puppy. We get our costs of integration, and then we go and impose our two boundary conditions of y equals 0. The first time we find out that shows that C2 is 0. The second time we find out a different value for C1, and then we plug it in and rearrange, and that's our equation for the elastic curve. This is y of x. Okay? Now that we have that, we then can go figure out, set that the derivative of that equal to 0. Once again, we already know what that is. If you just take that slope equation we already calculated, then that's what we need. Set that equal to 0. That gives us a position of the max deflection. We then can go back to our deflection equation shown here, plug in that value of x at the maximum, and that will give us what the actual maximum slope is, deflection is. And remember, this is only valid between A and B. To be sure that that's actually the maximum, we would have to do this whole process again for the segment of beam from B to C and find out if that deflection is more or less. It could be either depending on the relative geometry. All right. Just a quick review of singularity functions. Remember, I gave you this table last time. This table in your handbook gives you everything you need. It tells you what the functions are. The leftmost column is a singularity function for each piece of load. Now, actually, you can use this also to jump over to bending moment or shear and just grab those functions as well. However, because the integration is so simple and because repetition tends to make us make less errors, I recommend sticking with just write the equation for the loading here using only the first column, integrate once using the integration procedure here. It's rather simple. Integrate again, then we got the shear and moment. Integrate again as we divide by EI for the slope. Integrate again to get the equation for the deflection. Impose two boundary conditions to calculate the C that sprang into being when we integrated for the slope, and again to find the constant of integration that sprang into being when we got integrated for the deflection. Okay, that's what this is the same thing we used last time. This is a quick look again at our discontinuity functions. This first part is all stuff that was shown on the other slide. This latter part is what I wanted to show you, characterizing or idealizing functions. Once again, we talked about that a little last time. If we look at this lower left picture, we see a loading on the beam. If we wrote a free body diagram for that, we would replace the constraint at A with just a vertical force. We would replace the constraint at B with a vertical force. We would have our moment, and we look in our little handbook and we don't find a term that has this trapezoidal distribution. But we do have one that has a rectangular distribution. So the first thing we do is say, okay, we're going to idealize this loading because we have a term for this guy, so we can write that term. We have a term for this guy, we can write that term. We have a term for this guy, but we don't need to write it since it's at the right end. We don't have a term for this trapezoidal loading, but we do have one for a distributed load, so we write that term. And then we say, oh, we do have a term that increases from here to here. Now the trick here is we say, okay, this may be 6 kilonewtons right here, but this was 3 kilonewtons here, and since we already have this function accounted for with a separate term, because we have this is that term, and this is that term, and this is that term, so that's gone. So that means this loading, this dimension here is just 6 minus 3 in this case, right? That's the value we're going to use for our last triangular term using the singularity term for a triangular loading. The result looks like what's shown over here. First, it helps if we draw that with our reactions, our moment, our distributed load, and our gradient load. You got all that? That's how these are solved. That's called I call that characterizing the loading. We're characterizing the loading so that it exists in our handbook, in the table that we have. Here's another little example. Let's take a look at this beam here. Looks pretty simple. If we want the max deflection, we can just go ahead like this. We take our free body diagram of our beam. That means we calculate our reactions, draw them and the beam. We write our loading function. We've got a term for the leftmost force. We've got a term for the reaction at A. We've got a term for the moment and the reaction at B, but we actually don't need either of those terms. So let's just blow them straight to hell. Since they are here at the rightmost end of the beam at 30 inches, they're not needed. We can just ignore them altogether. Gives us a simpler function. We then integrate that puppy. You'll notice integrating when the exponent is negative just brings this whole thing forward and ratchets that exponent up, as we see here. Let's go through this. Taking a look systematically, we see that this term just changes this exponent to 0. We look at this term, since this is negative, exponent is 1, now minus 1, all it does is increment that exponent to 0. These next two terms do the same thing, but we don't need them, This cost of integration also goes to 0, so we don't need that. Okay? We then integrate again. Oh, we can impose a boundary condition. This is shown just so you know how it works. Impose a boundary condition, we find out that CV is 0. You don't even need to do that because I told you it's 0. Okay? We then integrate again, which means, once again, we're looking at this thing and we say, okay, looking at this term, that's now 0. So we use the rules of integration, which all it ends up doing is throwing a 1 up here and dividing by 1. Same thing here. And then these two terms aren't needed, and we said this term is going to be 0 as well. If you really feel like calculating it, this is how you would do it and find out it's 0. We then rewrite our moment, is a clever and handy thing to do, and then we integrate it again. If we integrate it again, we get now when x, you're going to see something here. When x, when we see this function here, this is the same as minus 8. Now whenever we have a 0 here, whenever this term is x minus 0 and this exponent is greater than 0, then actually we can just write minus 8x. And some books will do that because now that has sprung into being. It's always valid in the beam, and because we no longer need the exponent since it's now greater than 0, it will give you correct answers. I don't actually recommend that. I think you should keep this shown as a singularity term in this form here for the entire piece of work, not switching it to an 8x until you're actually calculating numbers. You'll find if you follow my advice on that, you will tend to make fewer mistakes. Okay, so we integrate that again. This is a rewrite of that function. We integrate again, we get a constant integration. We integrate again, we get another constant integration. We then can go and look at our boundary conditions. Now you'll notice that the deflection y is actually shown as v here. This is Hibbler. That's the nomenclature he uses. So when you see v here, that the little v actually is simply the deflection. Okay. So we plug in our constraints that at x equals 10 we have no deflection, and at n equals 30 we have 0 deflection, and that gives us our two constants of integration. We then plug them back into our equations and simplify to get the equation for the displacement and any other equations we need. We then can go and use the slope equation to find out where the deflection is maximum, plug those values in, and get what that value is. That's continued here, and that's how it works to calculate the max deflection. Okay. Now, since this beam has two spans, if you use continuous calculus with successive free body diagrams, you'd have 2-moment equations. You would have to deal with both and evaluate them to find out which one of those provides a max deflection. If you use singularity functions, it's quite a bit easier. Here's another example. Given this beam here, once again we look at this thing and we say, oops, we're going to have to characterize this loading because it doesn't go, this distributed load doesn't go to the end of the beam. Looks like a simple characterization. So we start off by taking that 8 kilonewtons per meter and driving it all the way to the end, because once you turn those puppies on, you can't turn them off without giving it a cold shower, as you see down here, the minus 8 kilonewton per meter. We also don't forget you need those reactions. That wall at the left end imposes a constraint on both the vertical deflection and the moment, so both of those are going to be needed. You're going to need to calculate those values. To solve this, then you can, once you have a free body diagram showing everything, you can move from left to right and write the singularity function for each and every thing you find. Starting with the shear force, that's our first term. The moment, that's our second term. The distributed load that goes to the end, that's our third term. The moment at B, that's our fourth term. And then the cold shower distributed load, which starts at point B, that's our last term. We then can integrate that puppy and note that any constant of integration will be 0. Notice that we didn't write a function term for that 12 kilonewtons since it's the right end. We integrated that puppy and ignored the constant of integration since it's going to be 0. Integrate that puppy again and ignore the constant of integration since it's going to be 0. That gives us the moment. Now to calculate the slope, we're going to divide that moment by EI as we integrate. First, we're going to simplify like this. Okay, now we integrate again. That gives us the slope, and integrate again. That's going to give us the deflection. We've got 2 undetermined constants of integration. Now, we could have made this a little easier. After getting the equation for the slope, we could have plugged in that the slope at 0 is 0 and immediately gotten what C1 is. Or we can do it later, noting that the slope is 0 at x equals 0. That gives us that first one, and the deflection at 0 is equal to 0. That gives us the second one. Rewrite and simplify. That gives us the equation for the deflection. Got it? That's how it works. Your Beer-Johnson text, supplementary text, and any other undergraduate structure mechanics and material text will have a lot of examples of beams. You can actually try this procedure on any of them, and you should be able to match results. It's good practice. Enjoy.